Alright, so in this lecture I want to introduce the second kind of fundamental definition in calculus, namely the concept of the definite integral. So let's recall what we did last time. So we went through a pretty elaborate procedure to try to understand areas underneath curves. So if I give you a function f on a closed interval a to b, and we assumed during that exposition that I was positive, so I was greater than or equal to 0 for all x in the closed interval AB. So what we saw was the following. We went through this very elaborate procedure to determine what the area was bounded by the curve and the x-axis between x is equal to a and x is equal to b. And what we found was the following. The area bounded by the curve y is equal to f of x and the x-axis between x is equal to a and x is equal to b. Well, it was this pretty elaborate thing. Remember what we did? I'll draw a picture in a second, but I'll just write down kind of formally what it was. It was the limit as n approached infinity of a sum of areas of very specifically chosen rectangles. So the sum was from I is equal to 1 to n of f xi star delta x. So this thing, remember, was called a Riemann sum. A Riemann sum. So rather than just say in words what this was, let's just think of a picture. If I have a function and I chose n to be equal to 4, what I'm basically doing is using n rectangles to approximate this, and each of these individual things is the area of one of these rectangles, this being the base and this being the height. But more explicitly, this was the picture that we came up with. So for n is equal to 4, this is what we have. So you take the base, you divide it into 4 pieces, each equal length. So that's what the capital delta x is. It's b minus a divided by n in general, b minus a divided by 4 in this picture. So that divides it into 4 subintervals, and in each subinterval you choose kind of a sample point, xi star. You can see them at the bottom, they're in green. And then you look at the value of the function at those points. So in this situation, it would be the height of these green lines, and then you draw rectangles with height given by these green lines, and you sum up the areas. So this is the picture for n is equal to 4. For n, you have more. So what's the basic idea? Well, as n gets really big, these rectangles get narrower and narrower and narrower. And because it's getting so narrow, the error between the true area underneath the curve and these rectangles, or the sum of these areas of the rectangles, is going to tend to 0. So just as an example, just to make sure we really understand, this rectangle here, in the above notation, this has area equal to f of x, I think it would be 2 star, wouldn't it? Delta x. And your delta x is kind of the length of any one of these guys. So this is delta x is equal to b minus a divided by 4 in this case. So this is an incredibly elaborate procedure to come up with a really precise way of understanding what the area under a curve is. Now let's take a look at this guy here. Now all of this was done with f of x positive, right? Because I was thinking about the area underneath the curve, or enclosed between the x-axis and the curve. But if you look at this, at no point in any of this construction really did we need f to be positive. I mean, this would still make sense. You could still divide the base into pieces and then choose sample points and evaluate f at them. Now these could become negative. So let's kind of think about what happens in that case. So let's make an observation. Or maybe let me repeat what I've just said. So observation. This limit, so rather than write that out again, let me just copy it. This limit here, this makes sense. It makes sense, even if f is not positive on the interval AB. It's just kind of a sum of things, and I'm taking a limit over that sum. So let's think a little bit about what would happen if I was negative, for example. So let's assume for a moment, let's assume that f of x is less than or equal to 0 on the interval AB. Well, what would this sum correspond to? So we have the same basic construction, but we've got to be a bit careful. So let's kind of go through it quite carefully. I'll do it for n is equal to 4 as usual. So I have my interval between a and b. Okay, I divide it into 4 pieces, all of the same length. Okay, so this is equal to x0, this is x1, this is x2, this is x3, this is x4. What else do I have? Well, I have a curve of some description. So let's just kind of draw it like this. Now it's underneath the axis. Yeah, so I should do it in the same color as before. So it's going to look like something like this, isn't it? So it's underneath. And let's go through exactly the same procedure. Let's choose sample points at all of my positions. So I'll choose a point here. So I'm going to draw these lines down, and I'll show you in a second. Point in here, point here, and a point here, let's say. So this would be my x1 star from above, this is x2 star, this is x3 star, and this is x4 star. Now, what was I interested in before? It was rectangles, wasn't it? And the rectangles in the above were kind of above the axis, but I could still draw rectangles below. So let's go through exactly the same procedure. So let's take this, paste, change the color. So let's draw the rectangle down here, which has that height. Same story. So the first rectangle would be given by this, I think. Oh, sorry, I've made a mistake. I put it in the wrong position. It should be here, shouldn't it? Easy mistake to make. I think I did it last time too. Okay, so that's one rectangle. So we've not related this back to this at all yet. We're not quite sure what's going on, but I'm just drawing these rectangles to see what happens. So this guy, let's do a copy, paste, style, let's do red. Same story. So this is time consuming, but it's worthwhile doing very carefully to begin with. Of course, same story. Then what? Let's do this guy. I should copy it first, shouldn't I? Next one here. We're all going to be pretty sick of doing this by the end of these lectures. Okay, and finally this style, let's do red. Okay. Now the area of these rectangles obviously would be a reasonable approximation for the area underneath the curve. But remember what I'm interested in. I'm interested in this expression here. This is the one we've looked at. This is where it kind of all started. So I want to kind of relate this back to these rectangles. So let's make an observation. Everything underneath the curve, well, they're all negative values. So f of xi star is not the height of the ith rectangle anymore. It's minus the height because it's underneath the axis. So what does that mean? Well, that means the expression that I have in the above, this f xi star delta x, Well, the length is the same, the base is the same, that's positive, it's fine, but now I'm multiplying by minus the height, so this is not the area, it's minus the area of the ith rectangle. It's minus the area of the ith rectangle. So what does that mean? Well, if I sum them up, these expressions, that's going to be summing up negative of the areas. So I think I'm going to get kind of the same story, but everything's going to have a -1 in front of it. So this implies if I take the limit as n approaches infinity of these expressions, fxi star delta x, well, these are all minus the heights of these rectangles. As n gets bigger and bigger and bigger, you're approximating the area to higher and higher accuracy, but everything's negative. So this is minus the area bounded by y is equal to f of x, and the x-axis between x is equal to a and x is equal to b. So this expression, this limit of Riemann sums, does make sense, but the moment I dip onto the axis, or if I'm negative the entire time, it's not the area, it's minus the area. So I think we can see from this what has to happen in general. A function generally isn't always above the axis or always below, it's a combination of both. So taking these things, so first of all the above example and the below example, putting them together, I think we see the following. So more generally, we have the following. This limit, so where am I? Oh, sorry, I made a mistake here because it should be a sum. This limit would be 0 otherwise. It's such an elaborate expression, it's always a nightmare to write down each piece. So you're summing over these, remember, that I is equal to 1 to n. So this limit of Riemann sums, copy, is going to be equal to what? Well, it's going to be the net area enclosed, and I'll have to explain what that means in a second. I just want to get this down. This is going to be the net area enclosed by y is equal to f of x and the x-axis between x is equal to a and x is equal to b. Now what does net area mean? Well, let me just show you. You can probably guess from what we've just done. So I'll just do it with a picture, because a picture says everything you need to know. So if you have a function which is above and below at different times, so something like this, for example. So imagine if this is y is equal to f of x. Well, you've got two types of region enclosed. You've got the regions above, so things like this. I'm always going to use red from now on to indicate areas enclosed above the axis. And for those of you who are colourblind, I'll use green, but I'll switch the direction, so it's not a problem. So the total region enclosed is basically the area of all of this stuff. When I say net area, what I mean is the following. It's the area above minus the area below. Now you see why I'm doing this. It's because this Riemann sum business counts areas above the axis positively and it counts areas below negatively. So this sum does make sense and it is related to areas, but it's a bit more subtle. It's not kind of what you might immediately think. It is the net area, so the difference between the area above and the area below. So just to recap, this sum makes sense basically, assuming the function is reasonable. We'll talk about that in a second. Now if the function goes above and below the axis, you can interpret it in terms of areas. It's the area above minus the area below. Minus though, very important. So here we go. Here's our fundamental definition. Where am I? So this is up there with the derivative. It's one of our two core ideas in calculus. So first of all, I need to be a bit technical. We say that a function f on a closed interval ab is integrable. If, well, this limit makes sense. First of all, the limit as n approaches infinity of these Riemann sums so this is I is equal to 1 to n f xi star delta x. If this exists, remember it's a limit, so it may not exist, so it has to exist, and slightly or delicately, it has to be independent of the sample point choices. So if you chose different sample points, yeah, the Riemann sums would be different, but the limits would be the same like we talked about last time. Is independent of sample point choices. That's what integral means. Really, intuitively, what that is telling me is the concept of area is reasonable. Being integrable says the area above and below makes sense and the difference makes sense. So this is basically saying, basically means the concept of area is reasonable. Concept of net area anyway. There are functions which are completely insane and there's no easy way to think about areas. I think I maybe talked about one last time. If you take, say, a function which is defined to be like 0 on rational numbers and 1 on irrational numbers, that's such a bonkers discontinuous function. This limit wouldn't really make sense, right? And neither would the concept of area because it's such a weird, completely impossible to graph function. Okay, so in this case, this limit is given a name. In this case, we denote this number. So it's just a number. It's very important. So what is it? It's a limit of a sum. So we write this as kind of an elongated S, which is an integral symbol it's called, with an A and a B here to represent the fact we're doing over the closed interval AB, f of x dx. This, by definition, is the limit, well, it's exactly what I've written above, limit as n approaches infinity of this. So this is just notation. First of all, just like dy over dx is just notation. What is it called? It's called the definite integral. Called the definite integral of f on AB. So this is a very formal definition of the definite integral. Integration. It's an interesting word. Where does integrable come from? Well, integration, is the idea of one thing coming from many. So putting together many pieces to form one. And that's exactly what we're doing here. We have one object, some sort of region we want to know the area for, and we're approximating it using smaller pieces. So we're joining them together. So this is kind of from one, many. One from many, if you want. That's the reason this terminology is being used. Just to give you some indication of where the word integral or integration is coming from. Okay, so it's not really different than what we've done already, it's just we've given a fancy name to it. So the story is, I'll just write this down more carefully. So the picture, just as before, is the following. But I'm going to come up and steal everything I did a moment ago. This guy, copy. Well, now net area, fancy word for net area is the definite integral. So this is my new notation for this net area. So it's just notation for the net area. Okay, so first of all, its net area could be negative, right? Areas are always positive, but net areas are not necessarily, because you're taking away. So this could be a negative. That's first of all. Other things, well, this condition of being integrable is a bit of a nightmare, right? You've got to check this limit exists. It's really complicated. Thankfully, reasonable functions are integrable. So a useful fact or an important fact, if f is continuous on the interval a, b, that means it's integrable. That's pretty hard to show, but it's true. In general, there are more functions that are integrable than continuous. For example, if you're piecewise continuous, you're integrable. But yes, so we've got tons of integrable functions. It's a condition you don't really need to worry about ever. If you were to do a more sophisticated class on mathematical analysis, so something like Math 104, you'd kind of think about this quite a lot. Okay, so I just want to point some stuff out. It's super duper important you understand this is the net area, which is a common misconception, so this is important. Important. This is not the same as the total area enclosed. That's the total area enclosed by y is equal to, well, y is equal to what's f of x and the x-axis between x is equal to a and x is equal to b. It's not the same. What is that? That would be the area of the red, if I'm using the above picture, plus the area of the green. So that's a completely different concept. They're related, obviously, but it's not the same. So the definite integral is a net area. Very important. So this is net area enclosed. So an interesting question is, well, can I use this concept to get a net area, or to get a total area instead of a net? There is a pretty slick way to do it, although in practice it's not so useful, but let me just show you. So let's take this example. Now, the problem is that green is being counted negatively, and I would like to count it positively. So what I want to do is flip that thing from the bottom to the top. Now, how can I do that? Well, there's a really straightforward way to do it. If I take the absolute value, it's going to turn all the stuff on the bottom to positive. So I could go through exactly the same procedure. So let me draw this, but take the absolute value. So if I take the absolute value here, what do I get? Well, it looks the same basically, except here you become positive, don't you? Something like that. So to represent the fact that's now becoming, well, I suppose it's becoming green, but if I reflect it, it's becoming red, sorry, but if I reflect it, it would kind of, at least, I think the cross-hatching would go in the same direction. Okay, so now if I was to take the definite integral of the absolute value, it's going to count the green positively. So the area, so this would imply, well, first of all, the integral from a to b of f of x dx, just as above, is the area where am I? It's the red minus the green. But now, the integral from a to b of the absolute value, well, it's going to be the sum of the two areas, because reflecting it doesn't change the area, so it would be the sum of the two. So it would be the area of the green plus the area of the red. So that's kind of a slick way of getting the total area enclosed, taking absolute values. The only problem with that, as we're going to see, is taking absolute values is a bit complicated because it does nasty things to functions. Okay, So this is pretty neat, but really all we've done is just come up with a definition, which is what we've seen before, and observed that this limit of Riemann sums actually is the net area if I'm going above and below the axis. So there's nothing too profound happening. Let's try and do something a bit more tricky. So let's think about the following. Let's express, so this is an example. Let's express this. So I want to kind of really make sure we really understand the format of Riemann sums. So I want to express this guy. So we'll do the limit as n approaches infinity. So this is going to look absolutely terrifying. I'm going to write it down. Of I is equal to 1 to n of minus 1 plus 3i divided by n cubed times 3 over n as a definite integral. Now this is a pretty horrific looking problem, but what have we got to do? Well, we've got to write this down as, we need to do the following, don't we? We need to basically express this as a limit as n approaches infinity of the sum I is equal to 1 to n of sum f x I star times delta x. That's what we need to do, don't we? So it stands to reason what we should try and do is make choices so that this piece and this piece match up. So what do we need to get this to work? Well, we need, I think, 3 pieces of data. We need to find an A, a B, that's not been given to me here, a function f of x, that's not been given to me, and I suppose my sample points, goodness, such that this term here this is equal to this term. If I can do that, then I'm going to be able to get a definite integral, because by definition this would be equal to the integral from a to b of f of x dx. So I said before, I think, there are occasions in mathematics where it's important that you can spot if something's a Riemann sum. I know we don't really have any ways to calculate definite integrals yet. We're going to see some next time without doing Riemann sums, so this seems a little bit pointless. But being able to recognize when Riemann sums turns up is actually really important, especially in things like physics and chemistry, really any mathematical sciences, they turn up a lot. Okay, so there are 3 basic things I think you should do here. The first is we need to piece by piece kind of pull information out. So the first thing I think we should try to do is to find appropriate, you don't need to do it in this order, but I think it's a good idea. We need to find appropriate delta x first. Now what is delta x? Delta x by definition is b minus a divided by n. Now let's take a look at what we've got. The way I've set it up makes this fairly obvious what to choose. It would make sense, wouldn't it, to have this matching with this. So let's make that choice. I should say there are many different ways to do what I'm about to do. We just want to choose the one that's least painful. So hence we should choose, let's choose delta x to be equal to 3 divided by n. It kind of makes sense by the way we've set things up. So what does this tell me? Well, this tells me the difference between a and b is equal to 3. Okay. Now I don't know what a is and don't know what b is yet, but I do know the difference is 3. So next, let's try to find appropriate a and b. Okay, so to choose appropriate a and b, we need to remember a little bit about some stuff. I think what we're going to do is to simplify our lives. This sample point is an absolute nightmare. What we're going to do is we're going to choose, we're going to hope this works anyway, choose xi star is equal to xi. And I'm going to do that because it's going to remove some of the complexity. It may not work, but let's give it a crack, right? So what do I know? Well, I know that xi is equal to a plus I times delta 3. That's a general truth, isn't it, right? So what does this equal to? Well, according to my information here, this would be equal to a plus I times 3 over n. So I suppose I could write this as a plus 3i over n. Now, let's look above. What do I want? I want to get an expression which is a function in terms of xi star. So I'm choosing xi star to be xi just because it's a sensible choice given the information given to me. So we're choosing this, and that's a good plan because in this above, or at least in this above, I can see an expression that looks like one of these, right? And I want a function in terms of that. So we can see, I think, a sensible, reasonably sensible choice. I think this guy looks very similar to this. So let's choose a as minus 1. So this is a tricky procedure. This is why I want to go through it. Hence choose a is equal to minus 1. If a is equal to minus 1, well, by step 1 I know that b minus a is 3, so that means b would have to be equal to 2, yeah? So now I've got my xi star, I've got my a, and I've got my b. All I really need is my f, so 3. Choose appropriate. Choose appropriate f. So finally, what have we got? Well, let's just put everything together. So we've got xi star, we've got delta x, we've got everything. So we need f such that, so what is it above? Such that minus 1 plus 3i over n to the 3 times 3 over n is equal to f of xi star, but that's now equal to minus 1 plus 3i over n times delta x, that's at the very top up here. Well, that's 3 over n. So I'm really close. In fact, I can immediately read something off. So hence choose fx is equal to x to the 3, x cubed. So what's the conclusion of all of this? The conclusion is this evil sum from the beginning is naturally interpretable as a definite integral. Namely, the definite integral from, what did I choose? Minus 1 to 2 of x cubed dx. Okay, so this is a tricky procedure. I really recommend you look through it very carefully. It's the kind of thing that turns up in tests, it's the kind of thing that turns up in homework. Like I said, I wanted to go through it really carefully because it's a difficult procedure. So finally what I want to do is just to gather together a bunch of really important properties of definite integrals. They're all pretty intuitive based on the notion of area. So properties of definite integrals. First off, well, the integral from a to b of f of x, what happens if I was to flip the a and b? Now, it's a bit of a strange thing to do because we've always assumed a is less than b, but if I do that, well, the formula still makes sense. It would just delta x would become negative. So this actually, if you're just using the formula really without thinking about things, you get this. And as I said, this basically is because the delta x on one side would be negative of the other. That's the only thing that would change in the construction. Okay, so the formula would be exactly the same. So it's kind of strange, but it's more than anything an extension of the notation. Next, well, the definite integral from a to a of f of x dx, that's automatically equal to 0. You can see that from several perspectives. One, the net area has got to be 0 because there's nothing there's nothing to do, right? But also because a minus a divided by n is equal to 0. So delta x is equal to 0. Third property. This one's not so obvious, at least when you think about net areas, but the integral from a to b of f of x plus gx. If you super carefully write this out in terms of limits of Riemann sums and apply your limit laws, this breaks apart into two pieces. So like I said, it's the sum rule for limits, really. More than anything else. 4. Well, if I take the integral from a to b of a constant times f of x dx, unsurprisingly the constant can come out the front. Why is this? Well, it's because you're stretching or shrinking an area horizontal or vertically, sorry, so that's what happens to the area. Or you can view this very formally. This is just the constant multiple rule. Remember, all these defined to be limits. So if you really want to be sure of anything, you've got to boil it back down to limits. Constant multiple rule for limits. 5. Well, here's something a little bit different. If I have a, b, and c like this, then the integral from a to b, I should maybe say a and b are often called the limits of the definite integral, which is a bit strange because limit means limit, but it doesn't mean it there. It means it's kind of the end points. If I do this, if I sum up the definite integral from a to b and then from b to c separately, this actually has to be the integral from a to b, oh sorry, from a to c, all the way along, of f of x dx. Why is this true? Well, it's just adding up areas. So if I have something like this, if I break it like this, so if this is kind of your a, your b, and your c, the integral from a to b is this region. The integral from b to c would be this region. So of course, the sum of these two is the total area underneath. So that's the basic reason it's true. To actually prove that is actually quite difficult. It's not so easy because the Riemann sum definition is quite complicated because you've got this join in the middle with a b, but it is true. Finally, there's kind of a natural comparison here. If I had, so f of x less than or equal to gx, let's say, on the interval a to b. Well, what does that mean? Kind of obviously, because the graph of g is above the graph of f, that means the net area enclosed by f is less than or equal to the net area enclosed by g. It's really obvious if they're positive. You've got to think a little bit more if they're negative. But it's true. So that's like a comparison. So very nice. So this definite integral is a really important concept. It's the kind of the counterpart, the derivative in the world of integration. Not that they're obviously related or anything like that at the moment, but yeah, it's a really important definition. So definite integrals are net areas, not to be confused with total areas.